Okay, you're given the function right here that f of x equals 1 over the quantity 3 minus x, and you're supposed to come up with a Taylor series for that function. And around a equals 2, and determine the interval and probably the radius of convergence. So here's a little table that helps you set that up, where we're going to let n go from 0 to infinity, although I stopped at 4. And we're going to use this formula for a Taylor series right here, where a is 2. This is x minus a to the nth. This little n here stands for the nth derivative. So when n is 0, it's just the function itself. So when n is 0, the original function is 3 minus x to the minus 1. And the value of this expression at a equals 2 is, put 2 in for x, 3 minus 2 is 1. 1 to the minus 1 is just 1. And n factorial, 0 factorial, is also 1. We just define 0 factorial that way. When n is 1, we have to find the derivative of this function. So you use the power rule, negative 1 down front. You might think this is going to be negative. Reduce the exponent by 1, but then you have to multiply by the derivative of the inside, chain rule. So all of a sudden this becomes a plus. And then if you follow the pattern for the next derivative, negative 2 times 1 is negative 2, but you multiply by the derivative of the inside, and that becomes a plus 2. And negative 3 times 2 is negative 6, because it becomes a plus 6. Notice how we're decreasing these exponents for each successive derivative. And then we evaluate the derivative at whatever value a we're looking at. In this case, a equals 2. So I put 2 into this first derivative, I still get a 1. If I put 2 into the second derivative, 3 minus 2 is 1, 1 to the minus 3 is 1, 1 times 2 is 2, and so on. And look what happens. Everything in this column matches what n factorial is. So when I use this table to substitute into this formula, f sub n of 2 is really just n factorial. And n factorial is in the denominator, and x minus a, or x minus 2 to the nth. So that's your Taylor series right there. It's actually a geometric series. So we could use a geometric series, or definition a over 1 minus r, where r is less than 1 in absolute value, to find the interval of convergence. But let's do it with the ratio test. So here's a formula for the nth term, x minus 2 to the nth. The ratio test says that L equals the limit as n approaches infinity of a sub n plus 1 over a sub n. So a sub n plus 1 is x minus 2 to the n plus 1 over a sub n, and that reduces to the limit as n approaches x minus, which is the thing that you use the geometric series test. But if I evaluate the limit, I get the absolute value of x minus 2, and the ratio test tells us that this limit has to be less than 1 in order for this series to converge. And so this is the radius of convergence, because we want, this is the definition of the radius of convergence, that x minus a, the absolute value of that, has to be less than some value here. That's the radius of convergence. If I want to find the interval of convergence, if x minus 2 in absolute value is less than 1, then that means x minus 2 is between negative 1 and 1. I solve for x by adding 2 to both sides. This is your interval of convergence right here. Now, what does that all mean? Let's go to board 2. Here's f of x, 1 over 3 minus x. That's this red graph right here. Here's the Taylor series. from the sum from n equals 0 to k, well, we're going to get k get really big for an infinite series of x minus 2 to the nth. Here I let k equal 1,000, so we're getting bigger and bigger. And here's a table where x of 1 has values between 1 and 3. I put the 1 in here so you can see here it doesn't really look like it's convergent. But as soon as I get into the interval between 1 and 3, like 1.1, I'm getting exact values for the Taylor series and for the original function. 2.99. Well, if I let k get up to here to 1,000, it gets pretty close. If k is less than, like down in here at 500, they're not really very close. But of course, I can let this get bigger and bigger and bigger. And that shows you that for these values right here, this Taylor series approximates the function values right there. But if you're outside that interval, not so close. Look at how these match up here. That blue curve is lying right on top of the red curve. But as soon as I get outside that interval, it doesn't happen. Okay, there you go. Hope that helped. If you have any questions, post a comment.